We've already learned how to write solutions to systems with no solution, one solution, and infinitely many solutions. And here we'll just reiterate one of those ways we write it in what we call this vector form. So we know we could list a solution, if it's x comma y equals 4 comma 3, as in this case. Let's just say our variables are x and y, and here we would have our equal sign, and these are our constants. So we could see here that 1x plus 0y equals 4. And here 0x plus 1y equals 3. And so this implies that x is equal to 4 and y is equal to 3 is the solution. Now here we're already in reduced row echelon form, so we don't need to worry about what the original system was that we're solving. And one way we could write that is like this. And this is not the choice way of doing this. Oftentimes we might write x comma y is equal to 4 comma 3 is our solution. But we often want to write it in vector form. Okay, and it makes it a little bit cleaner, especially if there's more than two variables. So we could just write x, y, that vector, equals 4, 3. And the components of two vectors have to be the same if they're equal, so x equals 4, y equals 3 is still the statement. Okay, that's already in vector form. We've written it like that before. But now let's look at what we would do with infinitely many solutions. So how about the system with infinitely many solutions? Let's consider this one right here. Again, we could call these coefficients of the variables x and y, or they could be x1, x2, or w and s. It doesn't really matter what these variables are called. If not given, I'll just refer to them as x and y. And again, here are our constants. Okay, so here we have in the first line the statement that x plus y equals 4. And in the second statement, we have 0x plus 0y equals 0. This isn't very helpful. This just says 0 equals 0, which is always a true statement. Doesn't give us any insight into the value of x or y. But it's a good check to make sure that logically the system has at least one solution. Now, this is in reduced row echelon form. If we want to recall what that means, each row, there could be any rows with zeros, with all zeros. Those will be placed at the bottom of the matrix. We see that that's our second row here. Every leading one in a row always occurs to the right of any leading one in the row above it. But since the second row is all zeros, the leading one here, there are no other rows in which there is a leading one, so that statement is not violated. Above or below any leading ones, we have a 0, which is true. This is our only leading one, in fact, in this matrix, and below it is a 0. There's nothing above it. So we're all good. And if we had any leading ones in rows below it, we just need to make sure that also above and below the leading ones, there would be zeros. Okay, this one here is not a leading one because the leading one by definition is the first one in that row. Okay, so basically my solution says that 0 equals 0 and that x when added to y has to equal 4. It doesn't tell me what y has to be. It just says that x plus y needs to equal 4. So I would need to know a value for one of those two variables before I could determine what the value of the second variable was. For example, if you told me y was 2, then x would have to be 2 so that when I add them together I get 4. If y was 7, then x would have to be -3 because -3 plus 7 is 4. So in our situation, we see that y is a free variable. In fact, the way we could systematically go about this is look at the first row. Where's the leading one? Well, it's in the x. It's the coefficient corresponding to the x column. Therefore, x is not going to be a free variable. X is going to be contingent upon the value of another variable. We go in row 2. There are no leading ones. We've run out of rows. Therefore, any column in which there is not a leading one is a free variable, and that in this case is y. There is no row in which the first leading one in that row is a 1. There is no row in which the leading one for the y column is a 1, and therefore we would conclude that y is free. So that's the way we could systematically go about doing it. We can logically see here that y is free to be whatever it wants to be, but then x will always equal 4 minus y. Okay, so I'm going to write that statement. I'm going to say y is free. That just means that it can be any value it wants to be. It's free. And so let's assign it a number. Let's say y is equal to some constant c. Well, you could sometimes use s or t. Sometimes you'll see people write that. But c is just some real number. We write it like this. C is an element of the real numbers. All we've done here is we've just said, okay, y is a continuum of possibilities. And we've just said, all right, assign it a value of c. I don't exactly know what number that is, but by saying y equals c, I've kind of fixed a value on that number line. All right, well, now we know that x has to equal 4 minus y, and since y is equal to c, x has to be 4 minus whatever that value given is. If c is 5, then x would have to be -1 because 4 minus 5. So let me write this now as a solution. So as in vector form, x is going to equal 4 minus c, y is equal to c, and I've written that in vector form. But I see that that vector depends on the value of a parameter. Okay, c is what we often refer to as a parameter. C is called a parameter. That's just a fancy word for c is a constant, but its value is yet to be specified, that we get to choose what that value is. So what I'm going to do here, the goal is to break this vector up into vectors that just contain the constants and vectors that just contain the parameter. So down here, if I think about c as 0 plus c, then I can actually split this into two vectors, the vector 4, 0, plus the vector -c, positive c. Now I have one vector that just contains constants and one vector that just contains the parameter. Now, what I will do is I'll factor out a c from the second vector because that's what both components share in common, and then I have a -1 and a +1 left. You can see when you distribute that back in, you get -c and positive c. And my solution, written in parameterized form, will look like this. Okay, geometrically what this means is that this system will consist of the vector 4, 0, right? So any solution for this system will always consist of the vector 4, 0, which points 4 units to the right. There's the vector 4, 0. Plus, it will be some multiple, any multiple, of the vector -1, 1. Okay, -1, 1 is this vector here. -1, 1 would basically be I could generate any vector on that line right there. So the way we could think about this is the function y equals -x shifted to the right 4 units. So that's why we often write it this way in this weird parameterized form, because it gives us a geometric sense of solutions on this line. Now, you can't just pick any multiple of -1, 1 because we see that we have to add 4, 0 to that result. So think about it as the line y equals -x shifted to the right by 4 units. Let's look at another example, one that's going to be in 3 variables. So we're not going to so much focus on the visualization of this, although we could. And now let's assume that we have variables x, y, and z, and their corresponding coefficients. And here we have our constants, and there's our equal sign. Okay, so first of all, it is in reduced row echelon form because, once again, any rows that are 0 are listed at the bottom. There aren't any. below any leading one, here's a leading one, there's zeros. And also above any leading one, there are zeros. So there is a zero above leading one in the y column. And also, okay, so there we go. We have that case. And the fourth stipulation being that I'm sorry, the leading one in each row is to the right of the leading one in any row above it, which is true here. Okay, so since I only have a leading one in the x and the y column, that makes z a free variable. So once again, what I'm going to do here is I'm going to say z is free. So I'm going to assign it a value, just like we did up here, where all we're doing is we're just saying assign z to be some arbitrary value. And in this first equation, we see that that says x plus 0y plus 2z equals 0. And in the second equation, we have that 0x plus 1y plus 1z is equal to 4. And I'm going to do exactly what I did up here. I'm going to write x. Well, if I subtract 2z, I'll have x equals negative 2z. Now, since z takes on this value, I mean, it's going to be negative 2c. Y will equal 4 minus z, which is 4 minus c, since we've assigned z that value, so we're just doing substitution. Now I'll write my solution in vector form and then break it up into a vector containing the constants and a vector containing the parameter. So x is negative 2c, y is 4 minus c, and z is going to equal c. So I don't have constants for x and z, but I could write 0 minus 2c, and for z I could write 0 plus c, which allows me to break this up into two vectors, 0, 4, 0, plus a vector containing my c's, negative 2c, negative c, and c. And lastly, I'll factor out a c to get negative 2, negative 1, 1. So that means the solutions to this system are any multiples of the vector negative 2, negative 1, 1 added to the vector 0, 4, 0. So this is my solution in parametric or parameterized or vector form. Now we could kind of do a similar situation here where we represent, or to be able to visualize what this solution means. If I think about this as the vector 0, 4, 0, that's 4 units along the y-axis, and then any multiple of the negative 2, negative 1, 1 vector. So negative 2 would actually put me back 2 units this way, then negative 1 unit in the y direction, and negative 2, so it's going to kind of point, it's kind of hard to draw, but first of all, it has to be 0, 4, 0 plus any multiple of the negative 2, negative 1, 1 vector. All right. Last condition or situation that we'll consider. Here we have 4 variables, so I think I'll just go ahead and label these x1, x2, x3, and x4. I could use w, x, y, z, but let's shake things up a bit. And these are our constants in that fifth column. So I am in reduced row echelon form. First leading one is in the x1 column, so x1 is not free. Second row has a leading one in the x2 column, so x2 is not free. Row 3 has no leading ones. I've run out of rows, and therefore any remaining variables that don't have a leading one in a given row are both free. Okay, so I have to come up with 2 values. First of all, x3 will take on some value. Let's call it s. And x4 will take on some other value. We'll call it t. So again, what we're doing here is we're just saying x3 can be any number along this continuum. Let's pick this number s. x4 can be any number along this continuum. Let's call it t. Now, let's write x1 and x2 in terms of those values. So we see in the first row that x1 plus 0x2 plus 2x3 plus 6x4 has to equal 0. And in the second row, we have 0x1 plus 2x2, plus 1x2 plus 1x3 plus 3x4 equals 4. That means that x1 is going to equal negative 2x3 minus 6x4. And substituting in the values for x3 and x4, this means we'll have negative 2s minus 6t. x2, similar process, we'll have 4 minus x3 minus 3x4. Substituting in for x3 and x4, we have 4 minus s minus 3t. And we're prepared to write our solution in vector form. So x1, x2, x3, and x4 is our vector. You can see this is going to look much cleaner than trying to write it out as an ordering of values separated by commas. It's going to be much more visually pleasant. And what I'm going to do is I'm going to kind of write this, I'm going to space things out because I'm going to break this up not into 2 vectors as we've done before, but into 3 vectors. The reason for this is because we want one vector with our constants, and then another vector with the variable s, and a third vector with just the variable t. And because we have s and t, we're going to create 2 separate vectors for those. So for x1, I see my solution is negative 2s minus 6t. I'm going to leave a little space here for my constant, which I know is 0. x2 is going to be 4 minus s minus 3t. x3 is going to equal s, so I'll just put that under the s column there. x4 is going to equal t. So as far as the constants in x3, there's a 0 there. I can always write a 0 in. And I can always write in 0t as well. Now for x4, I could write 0 plus 0s, and then plus my 1t. So I'm going to split this up into 3 separate vectors. Here they are. We will have 0, 4, 0, 0, plus, now just the variable s, negative 2s, negative s, s, and I'll put in that 0s there just as a placeholder, plus negative 6t, negative 3t, 0t, and 1t. I'll factor out a t. I'll factor out an s, so this will give me s times the vector negative 2. Here I have a negative 1. Here I have a positive 1 and a 0. Here I'll factor out a t, which will give me negative 6, negative 3, 0, and 1. And now x1, x2, x3, and x4 have been found, and we have this in our parameterized vector form. Now this just emphasizes that every solution will always contain the 0, 4, 0, 0 vector, but then we could add to the tip of that any multiple of the negative 2, negative 1, 1, 0 vector, and also any multiple of the negative 6, negative 3, 0, 1 vector.